Welcome to our 33rd class in the physics of materials course that we have been going through, and we will continue from where we left off last class. When I finished last class, I told you that what we had done was to pictorially see how bands of energy, allowed bands of energy and band gaps appear in materials as a result of the interaction of the wave vectors corresponding to the nearly free electrons and the periodic structure of the lattice. Okay. So, we had seen it periodic in a pictorial sense. We actually drew the periodic structure, we drew it all to the same scale in K space, we drew the reciprocal lattice in K space, we looked at the allowed wave vectors in K space, and we found that when you plotted both the information in K space, we could identify the locations where the parabola corresponding to the electron energies intersected the boundaries of those Brillouin zones, right. And at those points of intersection, the we said in a descriptive sense that at that point the K vector corresponding to those energies satisfies the condition for diffraction. As a result of diffraction, there is a distortion of the E versus K relationship in regions very close to the Brillouin zone boundaries. The result of this distortion is that we have specific values of energy that are now prohibited. Okay. So, as a result, we were able to see how allowed energy levels and band gaps originate in a material, alright. So, this is a fairly important understanding that we have now got of the material in terms of something fundamental in the material, and we were also we also incorporated into this picture the Fermi energy level, and that then tells us that given this band structure that is possible in the material and given the Fermi energy level that exists in that material, is it going to be a metal, is it going to be a semiconductor or an insulator. So, all of that information we were able to pull together. We saw it in a very detailed manner for a one dimensional solid, and then we also saw pictorially how the same information would begin to appear for a two dimensional solid, and briefly we saw also for a three dimensional solid how the Fermi surface interacts with the Brillouin zone. So, in this process we were able to see how a lot of the information we have learned over the last several classes, lot of the terms we have learned over the last several classes, how all of them come together and give us a very good understanding of what is happening in a material and how we describe it. So, in the present class what we are going to do is now that we understand that the interaction of these K vectors and the Brillouin zones leads to and this periodic structure leads to these energy gaps that appear, we will go through a calculation. We will see if we can actually calculate when we are going to have an allowed energy level and when we are not going to have an allowed energy level. So, it is this calculation that we will go through in this class, and in this process you will see what sort of an approach we can take to put numbers down to this problem. Okay. So, to do that we will start with a brief look at what is the system that we are going to evaluate, and then we will go about writing the equations down for that system and evaluating the system. So, basically we are going to have a series of potential wells. So, I am just drawing three potential wells here, and we will mark this as the origin of this diagram, okay, and this is the distance. And we will say that the periodicity of this structure is A. So, when we say periodicity, so we are basically saying if you start from here, we come down, we go through this structure here and then again come out here. Okay. So, we have to come back to the same location. So, that would be the periodicity of the structure. We will say that the width of these potential wells is C, this distance between these potential wells is B, right, and the periodicity of the structure is then A. So, we can designate periodicity as A here, which means from here to here is what it would be, it would come back to the same location. So, this would be the A that we are looking at, or if you are looking at from here, this would be the A. Okay. So, this is A or this is A, where we are coming from the same location to the same location here. So, therefore, this is A, this is the periodicity of the structure A. So, if you write this as the origin, this is basically minus B, and this is minus A location, and this is then A minus B. this is also A, right. So, this is the periodicity of the structure and all the details are now available here. We will say that the potential here is 0 is basically 0, and this is some V0 is the potential that is there. So, in other words, there are regions where the potential drops to 0, which is the potential well that we have, and then there are regions where the potential is V. So, this is the V0. So, and these are all relative numbers, so it does not really matter because we are going to look at relative potentials with respect to some scale. So, this is what we have, and we would like to see what is occurring in the system, what is allowed in the system, what is not allowed in the system, and so on. So, to do this, basically we are looking at a bunch of electrons which are now subject to this conditions, the conditions that are shown here. With respect to this, so to see what is the impact of these conditions on those electrons, we have to basically solve the Schrodinger wave equation for the electron subject to these conditions. So, it has some energy E, and it is faced with a potential V0 in some locations, it is faced with a potential 0 in some locations. So, with respect to that we will solve the Schrodinger wave equation. Basically we see that we have some specific boundaries where you can solve the Schrodinger wave equation on this side of the boundary where the potential is V0, as well as solve the Schrodinger wave equation on this side of the boundary where the potential is 0. So, these are two possibilities that we have. What we are going to do is we are actually going to do that, we are going to solve the Schrodinger wave equation where V equals V0, and we are going to solve the Schrodinger wave equation where V equals 0, and we are going to require that at the boundary these two solutions are give us the same value. Okay. So, this is based on our general understanding that such functions have to be reasonable, the solutions that we get have to be reasonable, which implies that we are going to say that it is going to be continuous. So, in terms of the value here and in terms of the slope here, the function on either side of this boundary, whether it is coming from the V0 side or whether it is coming from the 0 V equal to 0 side, the value should work out to be the same, and the slope of those functions or the derivative of those functions should work out to be the same. So, that will then give us two equations for this system. There is another, so that is how we would get two equations, and we will find that there are certain constants that we will need to figure out. Additionally, we have periodicity in this lattice, and there is a way to represent periodicity in terms of the wave function, and that periodicity will ensure that we can compare two other locations in the system which are then periodic, and then for those two locations we can again say that for those two locations we have to have the value of the function to be the same at the two locations and the derivative to be the same. So, in this process for two different locations we are going to get based on these two analysis that we have just described, we are going to get 4 equations. We will find that there are 4 constants in those equations which we can attempt to solve for. What we will see is our end goal is not to really solve for those constants, but this provides us the framework. We will go ahead and attempt to solve for those 4 constants, but we will not worry about the actual solution of those 4 constants. We will find that en route we will reach an expression, we will reach an equation which will now have certain values which are correct and certain values which are absurd. So, the range of values over which we are getting where the equation is meaningful will then become allowed, will represent then the energy allowed energy band, and range of values where the equation is no longer meaningful will then become the band gap. So, that is how we will see that this set of constraints and what we are solving with respect to these constraints gives us when we are going to have a allowed energy level and when we are going to have a band gap. Okay. So, this is what we are facing, and that is what we will see. So, we will set it up as though we are going to solve for all the constants, but actually we will not bother to solve for the constants, we will just use this as the framework to get us what we need. Okay. So, now we will look at a series of slides which will start with a diagram like this, and then it will solve a set of equations which will get us the result that we are interested in. So, this is the system which we have just drawn. I have just shown you again here. This is the width of the potential well that we have, and this is the periodicity of this structure that is showing up here, and then we have the distance between the potential wells. And again, as we had just drawn, this is, we arbitrarily designate this as the origin, and therefore this would be minus b, that is the width backwards, and then this is minus a, and then this location would be a minus b. If you just did it, you will get. And to put it down in numbers, v equals v0, which is this value, in the region minus b to 0. So, from here to here, minus b to 0, v is equal to v0. So, that is what is written here, and similarly V is equal to 0 for 0 to x when x is between 0 and a minus b, which is this region, right. Between 0 and a minus b the potential is 0, and this general approach that we are showing here is attributed to Kramer's. So that is what we are going to see. So what we have to do is we have to solve the Schrodinger wave equation. In this case it is a one dimensional system we are looking at. So the time independent Schrodinger wave equation, which we looked at in one of our earlier classes, is what is represented here. In this essentially it says that the total energy is equal to the potential energy plus the kinetic energy. So that is basically what it is, what it says. We have to solve this equation for conditions where the potential is 0 and for conditions where the potential is V0 as opposed to 0, and we will say that when we compare these results in terms of their derivatives, in terms of the actual value of the wave function as well as the derivatives of the wave function, based on that comparison we will be able to find out the solve and get ourselves the result that we are interested in. So when V is equal to 0, if you go back here this term becomes 0, so essentially this term has to equal this term here, okay. So this term will go away, so that is basically what you see here, h bar square by 2m minus h bar square by 2m d square xi by dx square equals E times xi. So if you rearrange it, you have the second derivative of the wave function d square xi by dx square is minus 2me by h bar square xi x. This can straight away be solved by examination, merely by examination, because you know any exponential function, if you differentiate it you will sort of get this, if you differentiate it twice you will get this, plus you have a negative value here, so that is why we need to set it up this way. So xi x of the form a exponent minus exponent I beta x plus b exponent minus I beta x will solve this equation. So if you just derive it, differentiate it twice, you will get the beta square showing up out here, and beta square times xi x is what you will get, and the beta square is this value here. Therefore beta is simply the square root of it, of this 2me by h bar square. So beta is what you have here, and the I takes care of this minus sign, and a and b are constants that we do not know what they are at this point, and we will need to determine it, okay. So this is how this equation works out, and similarly we can attempt to solve the time independent Schrodinger wave equation in under the conditions where v of x is actually v0, okay. So it is some finite value v0 which is not 0. So to do that we have to go here, we just rewrite the equation. So again it is h bar square by 2m minus h bar square by 2m d square xi by dx square plus v naught xi is E xi. So rearranging you get this 2m by v naught e by v naught minus e by h bar square xi x. Simply I have just taken these values and moved this to the side and then rearranged. Again this can be solved by examination, except that we will now get functions that look like this, c exponent alpha x plus d exponent minus alpha x. Please note that when we previously solved when v is equal to 0, we got solution like this. Now e power I theta equals cos theta plus I sin theta. So these are actually trigonometric functions which will essentially be sinusoidal functions, okay. So this solution is a sinusoidal solution, and that results because you have this I here, which comes again because you have a minus sign here, fine. So that is how these things are tied together. If you look at our new solution now in the presence of a potential V naught, the term alpha, which is similar to the term beta we had in the previous equation, it has this form root of 2m v naught minus e by h bar. Now clearly this value in here can be negative if v naught is less than e, and it is positive if v naught is greater than e. So if when v naught is less than e, or rather the energies of the electrons are higher than v naught, then actually this works out to be a negative value, in which case it is the same as saying you have a I out here, okay. So therefore so the square root of minus 1 will once again appear. So when the energy is greater than v naught, under conditions where energy is greater than v naught, this solution will also be sinusoidal, just the way the previous solution was, because there is a square root of minus 1 showing up in both these terms. On the other hand, when v naught is greater than E, or in other words the energy is less than the value of v naught, energy of the electrons is less than the potential that it is facing, potential v naught that it is facing, this will remain a positive value, in which case these are all the alpha remains a positive value and a real value, and therefore this equation translates to an exponential equation. So again we have two constants here, C and D, which we need to determine. Now let us before we proceed further, let us look carefully at what we have got here. Okay, so x is the location. Okay, so x is the location, so that is along the axis, so that is something that we can vary. Now alpha that we have here and also that we have here consists of this information here. It is 2 root of 2 m, so m is the mass of the electron, so that is fixed, h bar is fixed, the V naught that is there for that system is also fixed, and this energy is something that we are not yet sure of. It could be a range of energies, we will have to look at the solution for a variety of energies. Okay, so this is what we have. In other words, the alpha actually has many of the system details in it. The V naught is from the system and h bar is from the system, therefore it contains a lot of system details. Okay, so so it is not something that we have a lot of I mean there are not too many things that are unknown out here, except we will try out a range of energies here. C and D we have no idea what they are at this point, we will have to find out what they are. Similarly, if you go back to the previous solution that we had, again we see the same thing, the beta that we found there also has 2 m here, m is again something that is fixed, we do not have a choice on, h bar is fixed, so it is for a range of energies that we are going to check it, so that we will have different values of beta, but it is something that is again system based. So it is only A and B that we do not know out here, which we have absolutely no idea what they are. X and again is the dimension or the direction in a distance that we are or position that we are checking this function at. Okay, so we now have this solution, we have solved this, we have the general form of the solution for xi of x, both under conditions where V is 0 as potential and V is V0 as potential, and as I mentioned our intention is to actually compare these solutions at specific values at convenient locations and see what that convenient location helps us understand about the system. So as I said, for the solutions to be reasonable we require that xi of x be continuous, therefore at x is equal to 0, at that location x is equal to 0, we would like the function, the wave function of that at x is equal to 0 to be the same regardless of which direction you are approaching that 0 from. As we saw in our original in the first slide, we can approach it from the direction where the potential is 0, so that is why the subscript 0 is, or we can approach it from the direction where the potential is V, in fact V naught, but we will write it as V here. So we can approach, so we can have a value for xi at the position 0 when approached from the direction where the potential is 0, and we can have a value for xi when the position is 0 but when we are approaching it using the solution from the direction where V is the potential. And we will also require that the first derivative be the same, so same thing, we can differentiate the solution coming from the direction where the potential is 0, in other words we will differentiate the solution that we got when the potential was 0, and we will differentiate the solution that we got when the potential was V, we will substitute 0 in both those solutions and equate them. So we are saying that this is going to be required of the system for the solution to be reasonable. Similarly, we will also do this once we find out what the effect of periodicity on the lattice is, and we will incorporate the same thing with the periodicity. The value of the function is going to be the same in 2 different locations and the value of the derivative is going to be the same in 2 different locations. Okay. So the periodicity of periodicity condition under such circumstances has been shown by Bloch, a Bloch, he is credited with this. So he basically says that in terms of the potential we say essentially V of x plus A is the same as V of x when A is the periodicity of that structure. In this case we are saying that the wave function x plus A, xi of x plus A will be the wave function at xi times exponent minus Ka, where K is the wave vector, and this takes into account the periodicity and the interaction of the periodicity with the wave vector. So that is how this comes about, and that is the reason why we have this additional function. So if you put it in, that is how you will get it. Okay, so if you put in x plus A and you expand it, you should get this xi exponent Ika step coming out of the equation. So that is how this periodicity comes about. So therefore now we can locate 2 positions which are not originally in the previous slide we actually looked at x is equal to 0. So therefore at that point we looked at the solution from the same location, so to speak. Okay, so we were not really looking at 2 different locations, we were looking at the same location. Now we are actually looking at 2 different locations. We are going to look at a location which is x is equal to minus b and another location where x is equal to a minus b. They are comparable because of periodicity. So xi 0 is what we have here, so on both sides it has to be the same, and the differential of it at when you differentiate the equation on of the wave function on either side of the origin, the slopes should work out to be the same. So this is what we discussed. So based on the solution we have got for xi 0, we can actually once we incorporate x is equal to 0 into that solution, we will get one equation. Similarly, once you differentiate it and you put x is equal to 0, you will get another solution or another equation, and then similarly you can take the value of xi at a potential v at this location minus b, and if you equate, if you work out this expression, then the equation that you will get will be equation 3, and similarly again you differentiate this equation on both sides, you are requiring that the slopes be the same, therefore you will get equation 4. So therefore just looking at two locations, one is at the origin, so all of these two equations look at the origin, they are basically saying that the value of the wave function on either side of the origin should be the same, the slope of the wave function on either side of the origin should be the same, that is basically all it says, and on one side of the origin we have a potential 0, on the other side of the origin we have potential v. So that is what these two equations say. So simply using the solutions, if you do these equations, we will come up with two equations corresponding to these two. Similarly, what we are saying here, based on periodicity, the value of the wave function on one side at a particular location should be this term times the value of the wave function on at another location, again coming from one side which is potential equal to 0 to another side where potential is v, and the same thing, the slopes on either side with this factor thrown in should work out to be the same. Okay, so this is how we have got these 4 equations, and they directly relate to the system that we have just described. So if you go in here, if you just evaluate these 4 equations that I have put down here, for all these 4 equations I am simply taking the solution at xi is at v equal to 0 and the solution at v equal to v naught, and then working out these the left hand side and the right hand side of each equation. Okay, so for example, if you look at this first equation, okay, so we are simply saying that the solution on the side that is where the potential is 0 is equal to the solution where this on the side where potential is v at the point 0. So if you go back to what we just solved, we see that when potential is 0, okay, so we have this solution. In this solution, when you incorporate x is equal to 0, this term works out to 0, this term works out to 0, therefore these exponents work out to 1. So it's simply xi of x works out to a plus b, alright. So so xi of x at x is equal to 0 and the potential being equal to 0 is simply a plus b. If you go to the next equation, on the right hand side was xi of x when the potential is v and and at the position x is equal to 0. When potential is v, this is the solution, and when x is equal to 0, this is again 0 and this is again 0. So these two terms work out to 1, therefore this will become c plus d. So therefore saying that xi of when we put this equation down here, when we say that xi of 0 at the point 0 is equal to xi of v at the point 0, this simply means a plus b, this works out to a plus b, this works out to c plus d. So that is what we have, the first equation gives us a plus d, a plus b is equal to c plus d. Similarly, if you go back to those same equations and differentiate them, so which we will just do briefly. If you differentiate this with respect to x, you will get a factor I beta out here. So this will become I beta a exponent this parameter here, and if you differentiate this term, you will get minus I beta b exponent this parameter here. Once again, when you substitute x is equal to 0, the exponential parts will drop to 1, both of them will drop to 1. So therefore we will have I beta a and minus I beta b. If you take the this equation where v is equal to v naught and differentiate it once, you will get alpha c exponent alpha x minus alpha d exponent minus alpha x, and then if you put x is equal to 0, this will become 1, this term will also become 1. So therefore this will simply be alpha c minus alpha d. Okay, so if you go back here, so we are going to have on this side alpha c minus alpha d, and this side we are going to have I beta a minus I beta b. So that is how this equation will give us this equation that we see here, right. So you now understand how we are getting these equations. These two equations here look a little bit more complicated, but they are actually not. they are exactly the same procedure that we have followed for these two equations, except that we are actually using these bottom two equations, right. So you see where this exponent minus ika term comes here, so that you will see in all these places exponent minus ka will show up here, minus exponent minus ka shows up here, right. So that term shows up in both places, and we are just evaluating this function xi v at a position minus b, and we are also evaluating its derivative at that same position minus b, and similarly we are evaluating xi 0 at a position a minus b and its derivative at a minus b. Previously these were 0 and therefore we were able to remove several terms, but now they have some specific values because you have a minus b. So simply if you just do that, you will get the expressions that you see here. So the value of the periodicity condition will give us this expression that this equation that we see here, okay, and then when you differentiate it and you write again incorporate the periodicity condition and then differentiate it and expect the derivatives to be the same on either side, then you get this equation here, alright. So we now have 4 equations, 1, 2, 3 and 4 equations. Quite straightforwardly we can associate them with the wave equation and how we solved it based on the wave equation. I suggest that you go ahead and do these on your own just so that you see how they come about, but the procedure I have shown you is exactly the procedure you have to follow. You merely have to go through the numbers and you will find that this is what you will get, okay. So this is these are the 2 equations, the 4 equations that you will get. Now in these 4 equations I will again reiterate that a, b, c and d are the constants that we have no idea what they are, okay. Alpha and beta, alpha here and beta here contain system related details such as the depth of the potential well and such, okay. So that is what it contains in the mass of the electron, so that is what is contained here, and k is the wave vector, so that is what is here. Everything else is simply a mathematical term here, so to speak. So this is what we have here, and what we can do now is in fact now that we have 4 equations where we have 4 unknowns a, b, c and d, it allows us to use mathematical approaches to try and solve for a, b, c and d. However, I will point out that we are the mathematical approach we will take is to attempt to solve for a, b, c and d, but that is not really our end goal. Our end goal is merely to actually see what are the conditions under which energy we have permitted values of energy and what are the conditions under which we have forbidden values of energy. So this is simply a framework to help us get that information, okay. So we will proceed to try and solve for a, b, c and d, and at some point we will actually abandon that attempt and we will use an equation that comes up in that process because that itself is what is the information we are looking for. So to solve this, first of all we merely have to write these as a plus b minus c minus d equals 0, and similarly move everything to the left hand side appropriately, set it all to 0, and we have 4 equations in 4 unknowns. So therefore to solve this we have the mathematical principle that we require to approach we need to adopt is that the coefficients of a, b, c and d in these 4 equations, the determinant of those coefficients should evaluate to 0, okay. So the determinant of those coefficients should evaluate to 0. So for example from the first equation when you write this as a plus b minus c minus d equals 0, the coefficients are plus 1, minus 1 and minus 1, because these two will be on this side of the equal to sign. Similarly you are going to have plus I beta minus alpha plus alpha as the 4 coefficients of a, b, c and d once you move this term to the LHS and equate it to 0, alright. And similarly you do the same with these 2 equations, and so we will get a determinant that looks like this. So we, as I said, we have 1, minus 1 and minus 1, we have I beta minus alpha and alpha. If you look at the other 2 equations, this is how the coefficients will work out, okay. So the coefficients are all listed here, and so this is the determinant that has to evaluate to 0. When this determinant evaluates to 0, you can use that to solve for a, b, c and d, okay. So that is how we need to do it, and as I indicated, you can run through this exercise. I am going to show you all the steps involved, so you can look at these slides and try and solve it yourself, or you can run through your own solution and then compare it against the solution that you see here, alright. To do this we are also going to take advantage of these mathematical identities. The cos hyperbolic function of a value of x is simply half e power x plus e power minus x, and sin hyperbolic x is half e power x minus e power minus x. These are all standard mathematical functions, hyperbolic functions, and since you see e power x and e power minus x, and we also have them in our equations here, we have exponents some minus x and plus x and so on. So clearly there is scope for us to play around with these functions and represent them using hyperbolic functions. So that is the reason why we use it. So taking advantage of these functions as and when we need them, if you look at our determinant again, I have just rewritten our determinant here, I have not made any changes to this determinant, and we will simply designate these as column 1, column 2, column 3 and column 4. Okay, so I am just walking you through the steps so that you know exactly how we are arriving at our solution. So if we designate the columns of the determinant as C1, C2, C3 and C4, and then let us carry out, see our purpose is to solve this determinant, so we will simply carry out operations and replace C1 by C1 minus C2. Okay, so if you do C1 minus C2 and replace C1 by C1 minus C2, this is going to reduce to 0 because 1 minus 1 will give us 0, and similarly if you do C4 minus C3, so C4 gets replaced by C4 minus C3, so minus 1 minus of minus 1, so that becomes a 0 again, and finally we also do we replace C3 by C3 plus C2, so we will add minus 1 plus 1, so all these are allowed determinant operations. So you can see that by just doing these operations we are left with a 1 at under column C2, this becomes a 0, this becomes a 0 and this becomes a 0. Correspondingly all these terms will also change based on the same additions and subtractions that we have just carried out now. Okay, so just doing these operations you will get the determinant to be look like this. You have 0 here, you have 0 here and you have 0 here, you simply have 1 here. Okay, so now we can expand this determinant using row 1 because 3 terms are 0, so effectively we only have to expand using this term, and we can ignore these terms, so we will only have this and this and this incorporated in this determinant. We can expand the determinant using row 1, or in other words we can obtain its Laplace expansion. We see that the determinant now will evaluate to A12 C12. Okay, so first row second column, that is what A12 is, and C12 is the cofactor of this first row second column, which is simply the terms here multiplied by the appropriate factor in the front. Okay, so C12 is the cofactor of A12. So if you do that, so now we are going to simply expand about this A12 and about row 1, so this is what we get. Since A12 is 1, we can simplify our problem to simply evaluating the cofactor C12, okay, because A12 is 1, so we only now have to evaluate C12. So C12 is simply this, these 3 terms here, this set of terms here, this set of terms here and this set of terms here, times a factor in the front. So I have just put those terms down here, so it is now a 3 by 3 determinant, and the factor in term and the front is minus 1 power 1 plus 2 because we have the subscript 1 and 2. So we will effectively get a minus 1 here, but please remember again this determinant is still evaluating to 0, we are still evaluating the same determinant, our original determinant was set to evaluate to 0 and we are simply proceeding along those same lines. So since the determinant must evaluate to 0, we can ignore the constant minus 1 power 3 as well as the multiplicative factor 2 in column 1 as well as in column 3, right. So there is a multiplicative factor here and a multiplicative factor here, we can ignore those, so we can remove this 2 and we can remove this 2, all the 2's here, and so the determinant now becomes something that that is of the form that is shown here. So it is a 3 by 3 determinant, so it is much easier to evaluate. So again we will play a little bit because we can see here an I beta here and an alpha and a minus alpha and a minus I beta here, so it gives us room to further simplify. So we simply add column 1 and column 3 to column 2. Okay, so if you do that, the top term becomes 0 and the terms here become the what you see here, and you can see I have got the hyperbolic functions here, so that incorporates at different locations you see the hyperbolic function, and that incorporates the fact that we had those terms that we had that e power x plus or minus e power minus x, so that is how we got these. Okay, so now we can expand this determinant, so expanding it we get I beta times this big term here plus alpha times this big term here. So as I mentioned, I suggest that you go ahead and try this out because it is fairly straightforward. If you go through it once, you will feel very comfortable that you understand how this energy gap comes. So it is simply I beta this times this minus this times this, that is the first term, and then alpha and we will have this times this minus this times this. So that is all we are going to do, and so that is what you see here, this big expression here. In this expression we can take advantage of this mathematical identity, just like you have sine square theta plus cos square theta equals 1, if you take the hyperbolic functions, sine hyperbolic square of some theta minus cos hyperbolic square of the same theta is -1. Okay, so if you put -1 correspondingly here, so you have you have similar terms here, you see here cos square alpha beta and sine square alpha beta. So you are in a sine hyperbolic and cos hyperbolic, so you can simplify it, you get this expression that is out here. Okay, a much simplified expression begins to appear here. Again we can remove the constant, common constant I exponent minus IKA, you will find that showing up in all the terms, so you can remove this constant, and since it evaluates to 0 you can do that. Okay, so please note all along we have now expanded this determinant and it is equal to 0. Okay, so you can remove multiplicative constant, so we can remove this, so therefore the expression we end up getting is what you see here. Okay, so this is the expression that you end up getting after you do these two simplifications. You have expanded the determinant, incorporated this simplification and incorporated this simplification, you have got this equation that you see here. Now since the determinant evaluates to 0, we can regroup the common terms we get, and so we have and we can rewrite it in this form. Okay, so this is what we have done, and we can divide throughout by 2 alpha beta, we see a 2 alpha beta here, so we can just divide throughout by 2 alpha beta. If you do that, we get this expression cos beta a minus b cos hyperbolic alpha beta alpha b alpha square minus, actually this is beta square here, by 2 alpha beta, and you have these terms here equals 0. So this is the equation that we get. Okay, and since e power ika plus e power minus ika by 2 is cos ka, we can correspondingly convert this to a cos ka. Okay, so that is how we get the cos back into the system. So the equation is now what you see here. So this whole thing was equal to 0, so we just this is equal to cos ka, so the cos ka can come to this side, and therefore we get this equation. Alright, so this is the equation that we get. So now let us reassess what we have done. We have got an equation where we have alpha, we have beta, okay, and these are system constants. Okay, so where we basically have some but it has energy, both of them have energy incorporated in them. This has energy incorporated in it, this has energy incorporated in it. Okay, so one has a V naught minus E term and the other has an E term, so both of them have energy incorporated in them. This A and B are system constants, in the sense A is the periodicity of the system, B is the distance between those potential wells. Okay, so that is incorporated here, so that is something that is fixed for the system, so we do not have any variation there. And so effectively in this entire equation what we have that can vary is the wave vector and the energy values that you have available in this system. So that is what we can change, we can look at various energy values and so on. Okay, so we have an expression on the left hand side of this equation and we have an expression on the right hand side of this equation. So I have just rewritten this equation, I have just flipped it around, so this is cos ka here, and the entire expression that we just came up with is now written on this side. So as I mentioned, on examining the parameters present on the right hand side of the equation, alpha is this parameter here, h bar is a constant, m is a constant, and v naught is a constant. Energy is something that we can explore. Okay, we can try out various energy values and therefore various alpha values we can get. Similarly in beta, m is a constant, h bar is a constant, and various values of energy we can try out. These two came from our original solutions of the Schrodinger wave equation. So for both the parameters alpha and beta, the parameter that can be varied is E, the energy of the electron that we are examining. Okay, other parameters A and B are constant once a physical crystal structure and specific atoms are chosen to occupy those lattices. Okay, so that is all fixed. So what you will find is, if you actually evaluate this equation for a variety of possibilities of energy values on the right hand side, this expression on the right hand side will give you a series of values corresponding to this expression. On the left hand side we have cos ka. By virtue of its the fact that it is a trigonometric function cos ka, we know that this cos value can only be between plus or minus 1. Okay, so it cannot be outside this window, it has to stay within plus or minus 1 window. What we will find is based on the energy values you choose, this entire expression here will on several occasions fall within the plus or minus 1 window, and on some occasions this expression on the right hand side will evaluate to values which are greater than this plus or minus 1 window. So you may have, say for example, a 1.5, this expression will evaluate to say a value of 1.2 or 1.5 or some such thing for specific values of energy. So that therefore it gives us a situation where this becomes an absurd relationship, okay, or an inconsistent relationship. So this is interpreted to indicate that values of energy where the expression on the right hand side stays within the plus or minus 1 window which is required based on the expression on the left hand side, those are values of energy that are now allowed for the system. Those values of energy therefore form the band gap, they form the allowed energy bands of the system. The other values of energy where this expression here evaluates to numbers which are outside this plus or minus 1 window, and therefore to values that are absurd or inconsistent with the left hand side, those values of energy now represent forbidden energy values or band gaps, okay. So that is how we evaluate this equation. Therefore, so in other words we say here, therefore a window in the RHS is forbidden to the system, and that translates to corresponding values of energy being forbidden for the system, okay. So there are specific values of energy corresponding to this right hand side, specific values of energy that we can try on this right hand side, because that is the only real variable that we have on the right hand side. We can try values of energy and which will give us values that are inconsistent with the left hand side, with the requirement of the left hand side that it be between plus or minus 1. So we are able to see that, so this is the conclusion that we were interested in, this is the information that we were interested in. So although solving the determinant we could have continued on the process and tried to get ourselves values for capital A, capital B, capital C and capital D, we have not actually done that. We have used that framework, we have used the determinant that comes out of that process to give ourselves this equation that you see on the screen, so that the equation now tells us what are allowed values of energy and what are not allowed values of energy in the system, okay. So, so starting with a system where we had a periodic structure, we are able to actually look at the constraints placed on the system and incorporate the constraints in the Schrodinger wave equation, and in that process we have actually gone ahead and looked at the value of that Schrodinger, the solutions to those Schrodinger wave equations under conditions where the potential is 0 and the potential is V0. Taking these conditions together, we have compared the value of the wave function at the origin as well as at a periodic boundary and based on the periodic boundary requirement at two other locations, and then we have compared both, we have said that the solutions have to be reasonable, therefore the value of the function on either side of those locations has to be the same, and the value of the derivative on either side of those locations has to be the same. This gave us 4 equations, we attempted to solve those 4 equations and we found that we had a very nice interesting solution coming as a result of that process. Okay, so what we have seen in this class, to summarize, is that we have actually looked at how we can evaluate based on the constraints placed on the system, how we can evaluate and see what are values of energy that are allowed in the system and what are values of energy that are forbidden in the system. And therefore something that we drew pictorially in our previous class, where we previously drew something pictorially, is something that we are now able to come up with as in terms of numbers. So we will briefly see this on the board as we wind up this class. So we saw in our last class that we basically could draw energy versus K, and then at the Brillouin zone boundaries, okay. So this is minus pi by A and plus pi by A. We found that the free electron parabola was getting distorted, so we found that it actually showed a behavior that looked like this. So if we draw the next Brillouin zone, we just stick to 2 Brillouin zones and we should be done. So if you look at this, this is how it would be. Okay, and in this context we designated this to be a band, allowed energy band. This was a forbidden band gap, and this was another allowed energy band. So now, so this is how we were able to see this pictorially. We have now been able to do calculations which tell us in this energy scale, what is this set of values of energy that are allowed. So therefore what is the allowed band, and what is this set of energy values that are forbidden, and therefore the band gap, and then we get the next band. So that is the calculation that we have done. Okay, so we have been able to actually understand the system in a pictorial sense. We have also been able to understand the system in a detailed calculation based sense using all the quantum mechanical details that we would have to impose on the system. Okay, so we have got a lot of information about the system. We now understand how bands originate in the system. In high school we are simply told to accept that there are bands, and for the most part many of the things that we material usage that we do, that is the information that we require. We simply need to know what the band gap is, and many material properties we can say on that basis. Now we are able to see what is the basis, what is the fundamental reason why a band exists in a material. Okay, so this is something that we had not looked at before, we were not aware of before. I will also highlight one more thing. I mentioned this several times, that this looks like a continuous curve, but it is several discrete points, and so this simply means that this band is a series of discrete energy levels that are allowed. Okay, they are very closely spaced relative to the band gap values, or even the band extent of the band. So please always keep that in mind. This is a series of discrete energy levels which are extremely closely spaced, and then you have the band gaps. So we have now understood the origin of bands in a material, and this picture also we will see later will also help us understand the anisotropy in materials. Okay, so we have taken a lot of information, brought it all together here. In our next class we will look at utility of this information, and more insights that we can gain into the materials based on all that we have understood so far. Okay, so with that we will halt for today. We will take it in the next class. Thank you.